the ester drug, so it will be hydrolyzed most frequently, and it will be getting degraded very fast in the presence of water. This is what we are going to estimate and find out its acceleration stability, and we are going to have the expiration period as a model. So in this particular case, we are going to determine the shelf life of aspirin solution. This is subsequently added to a syrup using a accelerated stability studies methodology. So most of the drugs which we are going to have in the retail, they either they will be having a weak bases or weak acids. Most of the drugs and which are having insoluble in nature, and almost all drugs we need to give expiration date on the label. Without giving an expiry date, the label, it is not considered as a proper, and it will not going to meet the label requirement. So we cannot launch the product into the market. So before we are launching any pack on the label, we need to indicate manufacturing date, batch number, and expiration date. This is mandatory. Mandatory means without skip, you need to do it. This is not like a guideline. If you do it, okay. Otherwise, no problem. It is not like that. You need to bound to do it. The expiry date is a assurance given by the manufacturer. Those who are manufacturing the product, that if the product is taken before the expiry date on the label, so the dosage form fulfills the specification presented on the label. It means whatever we are telling that it contains 25 mg of aspirin, whatever we say it will fulfill that label requirement before the expiration date only. After the expiration date, the manufacturer is not responsible for not functioning of any drug. If somebody is taking or someone is selling the product after the expiration period, it is their headache, it is their problem. Patient should not take, because it may cause the damage to his body, and pharmacy store retailers should not sell it. If otherwise, if they are selling it, they may close the pharmacy store. This is a law, and because of that reason, we are giving on the label, and we will assure to the patient that before that expiration date, it is a responsibility to the manufacturer. After that, we are going to take any responsibility, we are not going to take. That's what they wanted to inform regarding the identity, strength, quality, and the purity. All these four aspects. All these four aspects may not be fulfilled after it will not be present after the expiration period. That is the reason we need to use the drug before the expiry period. Otherwise, we need to throw it out. And there is a proper dispensing and throwing mechanism which is prevailing in the pharmacy store, in our house, and in the manufacturing. Most of the times in the manufacturing, they may be incinerating it. In the pharmacy store, they need to keep in a separate track, and expired product, they need to take it until they are getting dispensed. And we need to use a proper mechanism where we are going to throw it out. Most of the times, it should not cause the damage to environment. So the drug content department ensures, the drug control department, it will be ensuring its drug content, how much it is present as a regulatory control, that every product released into the market should be evaluated and fix the expiry period, and then only they will be allowing to the allowing the product to enter into the market. So the technical term for the expiry date is called as a shelf life, and we have got two terms, which is a rate constant, half life, and shelf life. Here we are going to use the phenomena shelf life to determine the product expiration period. Most of the times in the previous cases of alkali hydrolysis, acid hydrolysis, I asked you to determine the rate constant and half life. Now I am going to ask you to determine the rate constant and the shelf life. Now, what is the shelf life? Shelf life is defined as the time required for the drug to reduce its concentration to 90%. It means whatever we are labeling it, how much time it is taking to get reduced to the 90%, then we are calling it as a shelf life. So it means we are allowing it 10% to degrade out of 100%, and the time we are going to note it down, and by doing the experiments and repeating it and validating it, after that we decide the expiration period, rounding up to the previous year. I told you, rounding up to the previous year, not to the next year, rounding up to the next year. It is the previous year and release comfortably into the market. So the evaluation of the shelf life is essential because if the stability of the drug and dosage form can be influenced by the normal environmental conditions. There are four which are present. One is temperature, another is light, another is oxygen, which is present in the air, another is humidity. These will cause the damage under the packaging conditions, like what packaging we are using, whether it is a plastic or a glass, and according to the storage conditions like temperature and light, where we need to store, whether it is dark or in the refrigerator or in the room temperature. Most of the times, the drugs like esters, example aspirin and procaine and paracetamol. So these are all some of the amides like chloramphenicol. They undergo the hydrolytic reactions, and the hydrolysis will be taking place in the presence of water, primary component. And the second one is we are having acid or base as a catalyst, that is a specific catalysis by presence of the H plus and OH minus ion. And the general acid base catalysis, where we are having a proton donor or any proton acceptor, hydrolysis will be keep on going. That's what we have already learned in the theory. Similarly, most of the drugs such as the ascorbic acid and the promethazine undergo the oxidation reactions, and they will be degrading by the oxidation, by the presence of oxygen and reaction with it in the environment. That is the reason we need to see its stability also. So as a result of the accident, drug may not be exhibiting the desired effect and may show the reduced biological response because it is getting oxidized. Hence the degradation and decomposition involved in the chemical alteration or the reaction of the active ingredient we need to determine. And the knowledge of this chemical kinetics about its rate constant and the half-life and the shelf-life, that will be helpful to us to predict the reaction rates and further evaluating the shelf-life. So we need to determine first rate of reaction, that is stability rate constant, and another one we are going to have a half-life, and we are going to determine the shelf-life. Most of the times we are also going to take not only this chemical stability and saying estimation and drug content estimation, we are also going to consider the appearance of the product, whether that is changing in its state, are there any change in the color, are there any liberation of the specific odor. So these are also we are going to take into the account when we are doing the accelerated stability studies. So in older methods, a product is placed at the room temperature in the refrigerator in order to mimic the shelf-life conditions, and the stability is evaluated long back when we are having around 5 decades before. But it takes a longer period of the time. We have already told 2 to 5 years it is going to take, depending upon how much expiry date it is having. Such a design of experimentation is time consuming. We cannot launch the product. So that is the reason, and we cannot get the money also because we are not able to enter into the market because we have not studied the stability. If your reaction rate is accelerated, we are making it very faster by having some of the changes like increasing the temperature. It's according to the Arrhenius concept. Every increasing the 10 degree temperature, there is a 2 to 3 times increasing the rate constant. So that is the reason we are conducting experiment with the higher conditions and finding the linear relationship of that particular condition with our degradation. And we will make it very fast in the short span of time. And we can extrapolate it to the normal temperature, normal conditions, and we are going to determine the stability method estimated in the short span of time. This is actually what is allowed by the pharmacopoeia also, and drug regulatory authorities like CDSCO in India and USFDA in America, TGA in Australia. You have got all the regulatory bodies. They will be following similar guidelines, and they are having the procedures in addition to the ICH and WHO. So the analytical method, what is we are going to use, it should be estimating either starting material or decomposed product specifically in presence of both. Then we can use that particular analytical method, and it should not have any interference of starting material and the degradation product, because both are appearing and say giving us the same picture. Then we cannot estimate that how much drug is degraded, how much is remaining. So we need to have a analytical method to estimate specifically the starting product or end product in presence of both. So that is the reason we call it as a stability indicating assay method. Stability indicating means it will estimate its degradation product also, starting material also simultaneously in the mixture. So this is actually what we need to do in advance before launching our product into the market. So the results of the accelerated decomposition are extrapolated to the room temperature or a specific refrigerated conditions. Then we assume that the drug reaction is a zero order or a first order by calculation of its rate constant at different time points, and we apply that particular rate order reaction and particular equations, and we estimate the stability. So the accelerated stability studies is an experimental design to evaluate the stability of a product by the accelerating the rate of reaction. Because of that reason, we are able to get the idea of shelf life in the short span of time, less than 6 months. So we need not have 2 to 5 years to wait. You may be asked the question, what is the importance and significance of accelerated studies? The major significance here is we are reducing the time of testing. We are entering into the market in the faster when compared to your regular testing in the real time studies or real temperature or refrigerator conditions. And in accelerated condition, we are entering, creating the economy. And you may be thinking that we are launching in advance. If it is not stable in the room temperature, what will happen to the patient? That is the reason we parallelly conduct real-time studies also in the regular room temperature. If any problem is coming, then we are going to get the product back. That is called as a product recall. So a more comprehensive pharmaceutical pharmacopoeial protocol is given in the evaluation of chemical integrity and physical changes, and the protocol is approved by the regulatory authorities, and we are going to use the same protocol which is having a changes which can measure the changes in the physical and chemical integrity. So we are going to use it for the determination of our shelf life. We are also going to have a test for sterility in the injections and eye drops and nasal drops and any mucosal delivery systems. And we test for the resistance to the microbial growth for the action of preservative, and toxicity and biological studies also carried out wherever it is necessary during the accelerated stability also, because I have already told you in the packaging we are using plasticizer. That plasticizers are carcinogenic in nature, and if they are leaching into the product, it will cause damage to the patient for causing the cancer. So we should avoid such thing by studying the toxicity also in the accelerated stability testing. And we can say that no, nothing is leaching and the leachable is also not having toxicity. Then only we can enter into the market with that package. If that package is not good and having any leachability of a color or a plasticizer and internal plasticizer, what methodology we have used, it is also not helping, then we are going to change the package. So this is actually what the importance in the accelerated stability studies for the launching of our product. Most of the times the recommended conditions will be depending upon the zone 1 to zone 4. So we are going to have in the zone 4B in our India. So it is having around 30-degree temperature and 65% RH when compared to remain conditions. If we want to launch to America or any another countries, we need to follow that condition only for testing the product. So most of the times influence of the temperature is a major phenomena in the accelerated stability testing when compared to remaining factors like your change in the pH, change in the light intensity, change in the oxygen concentration. So these are all the things which will be there. But according to the Harihanius view, he has proposed that established the quantitative relationship between the temperature and rate of reaction. He has told that K is equal to A into e to the power of minus EA by RT. K is a specific rate constant, it will give the degradation rate, and A is a frequency factor, also called as Arrhenius factor, and it is material related parameter also. And EA is energy of activation. This means it is a minimum energy which is required to get a degradation possible. Less than that, it will not cause any damage to the product. So if it is having a higher the energy of activation, more the product is stable. That's what we are going to see. So most of the times 85 kilojoules per mole is generally present in our case of the pharmaceuticals. And R is the ideal gas constant. It is a constant which is available in the literature. T is the absolute temperature in Kelvin. So if you are having all the parameters known, we can one unknown parameter we can estimate. In this particular case, we are going to estimate first A and EA by knowing the K and RT. R is known and A and EA is not known. T and K we are first either determining and calculating A and EA, or A and EA is known and we are going to determine K by using the T. So this is actually what the concept we are applying now. So the Arrhenius factor or a frequency factor is a measure of frequency of the collisions that can be expected between the reaction molecules, that is two reacting materials, in the energy of the activation, and the minimum energy that is required for the molecule that collisions give the useful products. That is in the case of damaging or degradation product. In the case of the formation, and the product is useful, and in this case we are going to have a damage. So in the case of first order kinetics, we know that it is concentration dependent. In the second order, it is getting two concentrations are required, and both the reagents are getting involved. In the zero order, immaterial of its concentration, it is getting damaged. So the same exponential equation we are going to convert into a log form. That is log K is equal to log A minus EA by 2.303 RT. This we are going to use it with base 10. If you are using a natural log, this 2.303 will not be present. And in the examination, they will be giving you the values, whether it in the base 10 or in the E, that is natural log base E. We are going to take the particular equation in the log, and we are going to use it for the calculation if you are getting any problem. This one you can use it and read it for, you can apply for the theory also, practical also. According to the equation, a plot can be drawn. If you see it, it is appearing as a y is equal to mx plus c, that is appearing. In that case, c is intercept, that is log a here, and y is equal to log k, and x is equal to 1 by t, and the remaining is EA by minus EA by 2.30 R is slope. It means that if you are able to plot log k on the y-axis and 1 by t in the x-axis, we are going to get the intercept log a, that is Arrhenius factor or frequency factor, and we are going to take the slope. And after getting the slope, we are having 2.303 constant, and ideal gas constant is known. We can calculate EA also. So if A and EA are known, if you want to put any temperature there to predict the room temperature, then you can get the log K. Once the K is known, you can determine the self life and off life. This is actually what the basic concept of this Arrhenius equation in determination and prediction of the self life. So most of the times EA is a slope into 2.303 into R, and R is equal to what we are going to put here in the case of this is 8.314 joules per mole Kelvin. So this is the one which you are going to use. And aspirin degradation, that is principle in this experiment. You see this particular one, it is acetyl salicylic acid. Salicylic acid is a carboxylic acid, that is aryl carboxylic acid, and it is having a methanol as a acetic acid, and it is having a salicylic acid. So salicylic acid reacting with acetic acid, salicylic acid is containing OH. In that OH we are having acetic acid getting esterified. Because of the presence of H plus or OH minus ions, we are going to have a hydrolysis reaction liberating salicylic acid and acetic acid. So initially, your carboxylic acid is containing this aspirin is containing one carboxylic group. It is going to react with sodium hydroxide also to form sodium salt of aspirin. And the second case, when it is degrading, it is taking another more sodium hydroxide to get reacted with it, because acetic acid is also getting liberated. So previously it is unavailable in the case of starting, but after the particular period of the time, it is getting changed. It is getting altered because of the degradation, and acetic acid is liberated. That is also consuming more amount of sodium hydroxide if it is degraded. If the product is not degraded, the initial concentration of sodium hydroxide, what is consumed to react with the COOH of aspirin, that will be same. But once it is getting degraded, and more acetic acid will be liberated, and we are going to have an increasing in the alkali getting reacted with acetic acid also. So we are rising, and till entire acetic acid is liberated and consumed. So we are going to have a rise in the alkali consumption, sodium hydroxide consumption. At the end, again, you will get a stable. That is a constant measurement. Requirement in this particular case is this practical cannot be done by you alone in three hours. We are going to divide into the 6 groups, whatever you are going to have in the laboratory. You are coming 20 batch, you are going to come. In the 25 batch, you are going to divide into the 6 groups, and the 6 groups are taking at different temperatures of the estimation and clumping all data and sitting together and getting a prediction of your next room temperature. It means 6 persons data we are getting collected in this, and one person, if he is doing and he need to take 6 practicals, means 6 weeks it will be done to get the same one. This is actually what the time consuming experiment. So you will not get in the exam in the practical, but you will be asked in the synopsis, and you will be asked in the viva and theory also, and GPAT and exam, it is very much important. Now, the requirement is a volumetric flask. Till now what you have got is a principle. I hope you are able to. We weigh 100 mg of the aspirin and transfer into the conical flask that is containing 100 mg of the aspirin, and we are going to add 2 to 3 drops of acetone or alcohol to increase the wetting. We have already seen if it is not get wet, it will tend to float onto the water subsequently. So we will make it wet by adding acetone and alcohol. It will not cause any damage to the aspirin because it is not reactive to it, and it will dissolve the aspirin. In that, it will make it wet. Then we add 100 ml of 0.01 normal HCl. In that HCl, aspirin will getting converted into salicylic acid and acetic acid. So we take 10 ml of the sample immediately without degradation, that is at the 0 point. We titrate with 0.01 normal NaOH. So it will give the starting point of your journey where you have got initial material is kept ready. After every 10 minutes, we are going to withdraw sample 10, 20, 30. So we are going to withdraw the sample, and we are going to estimate how much alkali is consumed. Because the sodium hydroxide HCl is added to the aspirin, acid hydrolysis will be present. Because of that reason, it is having degrading to the acetic acid, so sodium hydroxide consumption will be increased. So the same experiment is conducted at different temperatures by different groups. One team of your batch will be taking 50 degrees, and you are conducting all this. Another 6, 7. Somebody is having any doubt? Mahima, do you have any doubt?
No, sir.
Okay. So, in this particular case, we are taking 50, 60, 70, 80. We are going to distribute to the different people. They are going to use the water bath. In that water bath, they will heat their solutions, and they do the practical. So initially we determine the titer value of the bank titration using the 10 ml of 0.1 normal HCl, and that is 1 ml of 0.1 normal HCl is equivalent to 1.8 mg of the aspirin. So whatever which is present, which is specifically reacting with aspirin, that 1 ml of sodium hydroxide 0.1 normal is equivalent to 1.8 mg of the aspirin. This is actually 1 mole of sodium hydroxide is going to react with 1 mole of aspirin. According, based on that, we are going to have this equation and equivalent weight. So whatever the volume of the sodium hydroxide 0.1 normal consumed, you multiply that with 1.8, you will get how much is the aspirin is present in that. Or it is getting degraded by the sodium hydroxide, which is showing in the titration. Then we are going to have a report. This is actually what is being the procedure. Now we will see the data, because you are not going to do anything, and it will take the 6 persons and teams together. We are going to have. Now I will be showing you one more data, so that you will be having the reaction. The blank titration is HCl plus NaOH. It will give the sodium chloride plus water. That is initial, that is volume VB. And it means 0.01 normal of either we are taking it, equal volume will be consumed. At 0 minute, we are going to add sodium hydroxide and titrate with it. So we are adding HCl in the presence of HCl. It is consuming whatever the HCl is present and the COOH carboxylic group. So this one will be consumed. That means at the 0 point, C0 is the initial concentration of your aspirin, is C0 is equal to V0 minus VB into 1.8. This is the initial concentration of the aspirin. After the 10 minutes, you are going to add 2 sodium hydroxide molecules, because it is going to react with, one is with acetic acid, another is with salicylic acid, whatever it is present. So we are going to have that. So that we are going to take Vt minus V0 into 1.8. We are going to have how much is the degraded. That is called as a X. So the amount of the aspirin degraded X you can have. Then you can calculate the CT. That is concentration which is remaining at time T. That is 10 minutes is C0 minus X. So like that you are going to calculate at 20 minutes also and 30 minutes also. So like that you are going to have, if you see the data at somebody has taken at 40-degree temperature, they have taken. Similarly, another student has taken parallel data at 50. Some another student at 60, 70, 80, like that 6 batches have come. All the data I am going to give. One student has got like this. Initially blank is taken starting reading 0.5 and 10.5, 9.9 ml is the volume of sodium hydroxide is consumed. Without heating and nothing at the 0 minute. 10.4 ml is the starting 27, that is 17 ml is consumed. This is V0. The top one is VB. So V0 minus VB into 1.8, it you will get C0. Then you have got to 27.4, 45.4, 18 ml is consumed. So you are going to get the Vt minus V0, you are going to get into multiplied with 1.8, you are going to get X. That X is the aspirin degraded. So CT is the amount remained is C0 minus X. You are going to calculate that. Similarly, you are going to do for 20 minutes and 30 minutes. The same calculation which is placed here. So the blank titration 9 ml at 0 minute titer value of 0 is 1.7 ml. Initial concentration of the drug is V0 minus VB into 1.8. You have got a 12.78 mg is present in your sample, which has been given by the madam to you in that sample. So generally what will they do? They mix with sodium chloride or some other material to make you confused. So you are going to estimate how much is present. The first point is initial concentration of your drug which is been given. That you have got, it is around 25 mg. They split into 2 batches. I think 12.78 they have got. At 10 minute titration volume is 18 ml. So we have heated it to different temperatures. I have already told. For the 70 degree centigrade, it is having a 273 plus 70, it is having a 343. At 70 degree centigrade, the value is X is equal to amount of drug degraded is Vt minus V0. V0 is already present. You have got that value 17 ml. So you are removing it. So you are going to get how much is the drug degraded is 1.8 mg. Initial concentration is 12.78 mg minus 1.8 is degraded. You are getting 10.98 mg. The 10.98 mg is your drug remaining at 10 minutes. At 20 minutes, you are going to calculate the similar Vt minus V0 into 1.08. So 18.2 minus 17, 1 point into multiplied with 1.8, you are getting 2.16. So C0 minus X 2.16 is 10.62 is remaining. At 30 minutes, Vt is this. Again, you are calculating. Degraded is 0.54. At 30 minutes, remaining is 12.24. So like that, you are going to get decreasing in the aspirin concentration with the time. At a temperature, here it is 70. Are going to take at 40 also. You are going to take at 50 also, and 60 also, 80 also. Like that, you are going to have a different values. Okay. Now you need to calculate the K. K at 10 minutes, you are going to use this formula. 2.302 by T into log C0 by Ct. So 2.30 by T is equal to first point is 10 minutes. So log C0 is 12.78 and 10.98. You are going to get what is K at 0.014 minute. Here they have used the first order rate constant because I have already known that aspirin is following hydrolysis first order kinetics. Because of that reason, they have used this formula. So if you are having zero order, this log conversation will not be there. If it is a second order, the second formula, different formula will be present. So based on this only, you are going to have a examination some problems. In the next practical theory class, whatever we are going to have, you keep one pen and pencil and calculator, pen and notebook and calculator with you. We solve some problems. And we will learn, that is only the exercise we are going to do next theory we are going to have. Keep ready on Thursday. I hope we have got a theory class. In that we will solve all these problems. So how to calculate zero order, first order, second order. When we are giving a second C0 and Ct, and if it is a 0 and first and second, how you get values, these are all things we will know it. But at present, we are calculating only first order only because aspirin degradation is following first order kinetics. So this is giving 0.14 at 20 minutes. The degradation is 0.09 and at 30 minutes 0.013 per minute. So average K is equal to 0.0081 minute. So this is actually what it is given as a 40, but it is a 70 degree centigrade. You write it is a 70 only, not at 40. In the top also it is being written as a 40, but it is 70 degree centigrade. Now you need to take it Arrhenius plot. You know, you got the K, so you know the Arrhenius plot from the different persons. You are going to get a different persons. You are going to take a Arrhenius plot. So in the Arrhenius plot, what will happen? Say, for example, you have got the Arrhenius plot for the 40s, 50, 60, and you have got the values getting collected from the different persons. So these different people, they have given you the data. In that you are getting this is the 40 only because 008 is 40 only. At 40 only they have done. So 40 and T is equal to 273 plus 273 plus 40 is equal to 313. 1 by T, we need to take x-axis 1 by T only. That is the reason we are taking 1 by T of this second column. That is 1 by 313. You are going to get a decimals. In order to avoid the decimal, what you do on the x-axis and y-axis, you calculate, multiply with 10.0, 10 to the power of 3. So now you are getting integers to the not the decimal. So 3.19. It is good to plot. That is the reason you have done it. Don't worry. And in the K is what you have got the values. In the 40, what you have got at the top is 0.081. It is 40 only, but written at the top as a 313. You need to write. And you are getting the K value. and log k plus 3. So you are going to have how much you are going to have, that is 3 point, that is 3 is considering the 10 to the power of 3. Log of 10 to the power of 3 is equal to 3. So that is the reason you are loading log k plus 3, and you are going to have that value is pasted here, because on the x-axis, y-axis you are multiplied with the 10.3, 10 to the power of 3. So you are getting this value. Now you have got the k value and the t value. So you plot it. When you plot it, and you are going to have the equation like this: log k is equal to log a minus ea by 2.3303 or 1 by t. It is appearing as a y is equal to mx plus c. In that slope, m is ea by 2.303 r, and you are going to calculate the slope, which you have got is minus 4.79. So you are going to calculate minus 4.79. You are going to get minus of minus is plus 4.79 into 2.303, and gas constant 8.30. This is, you are going to get a joules per mole, not kilocalories, joule per mole, 91.71 joules per mole. This is your A. This is your EA. Now you are going to have intercept is equal to log A. So intercept value is, you are going to get 2.1. And now you are going to plot these 3 values and see your own intercept values, your own slope, and use that only when you are plotting now. You are going to plot this table and your own value, whatever you are going to calculate. Now I am telling you that if they are not falling on the straight line, you make a straight line in such a way that more points are falling on the curve, and either side of the point it will have equally. So you need to draw it with the center, the same rule which you need to follow here, and draw a straight line. So here 1 point should fall, and either side of that particular line you should have 1 on either side of that line. Then you are going to get a good fit, and you are draw it extrapolated to the y-axis. That intercept value you are going to get is A, log A. So log A is here is equal to 2.1, and the anti-log of A 2.1 is equal to 125.8. So this is actually what you are 1 by t. So 1 by t is equal to 3.36. In the y-axis, you are having a scale and you are having a k. So x-axis, you know, 1 by t is equal to 3.303. At 3.36, you draw a vertical line into the graph and intercept to the line. After intercepting to the line, you will be getting a point. You draw a parallel line towards the y-axis and predict k value. I repeat, you have got a line. You know the value of 25 degrees centigrade. That you are not done, because it takes months to get your data. So in 3 hours practically you want to get it. So you are not done 25. So but you are predicting it by taking 1 by t value. That is 1 by t here is 25 plus 273 is 298. 1 by t is equal to 3.36. This 3.36 scale in the y-axis, x-axis, you put a vertical line. It will be intersecting to a point in the linear line, and that line you are going to extrapolate to the y-axis, get the k value. That k value is here, it is presented. That k value is nothing but log k25 plus 3. That value is 0.25. So log 225 is equal to 0.25 minus 3. It is equal to minus 2.75. This minus is increasing. That is the degradation, the concentration is decreasing. That is indicating. So you have got the k value also. By knowing the k value, you are going to have this log of k value. You are going to have this value is 0.0018 per minute. So you calculate the T90. So for the T90, what is the formula? 0.695 by k is equal to half-life. 0.105 by k is equal to self-life. So 0.105 divided by k25, you are going to get 58.3 minute is your self-life for this solution, what is being given in your practical. It means it is within 1 hour, it is getting degraded 10%. 10% of degradation is taking place within that. Now what you don't have is a plot. This plot you need to draw now by